is 2817. Today we are going to start a new chapter. So review of lecture 10. We will have it briefly. So in the previous class, we have given you an example of one-dimensional. Okay, let me just save it. Lecture 11 of a bar, and we derived what is the stiffness matrix using the Galerkin method, and then we showed that for for two noded element how the K matrix is, and using that K matrix we solved this set of example, and we also talked about the properties of the K. This is the short brief description of what we have done in the previous class. So let me review it again. So first one is using Galerkin's approach, or what you call it as using weak form and the numerical approximation, we developed the stiffness matrix for the bar element. We showed that K for an element is defined as integral of dn by dx ae dn by dx. You can write it as transpose dx 0 to L is your K matrix, and constitutes of F naught, which is point loads, and F from the N P dx. This is from the distributed body load, and this is for the concentrated load. Anyway, let me see. I'm getting some comments. So audio is not visible, available. Can you hear me? Hello, can you hear me? Yes? Can you hear me properly? Can you hear me? Hello? Okay, I'll try to speak a bit louder so that you can understand. Um, Now, after this, what we have done, we show that for two noded bar element, for a two noded bar element, which is A and B, n of A, sorry, 1 minus xe by Le, n B, x, the shape functions, which is xe by Le, we showed that our K is defined as Ae by L 1 minus 1 minus 1 and 1, and using this as our stiffness element, Then what we did was we discussed the properties of K and Kg. K is and K, this is element stiffness, global stiffness matrix. From here to here we achieved it using assembly. Okay. After that has been done and we discussed the properties of the K matrix, we assembled the structure and we solved an example. We solved an example of with a point load P, A and E. This is 2A, 2E. I think this one is 3E. We solved it with the 3E. Let us see from the previous class. This is E and 2A. This is A and 3E. 2A and 2E. This is a length of L. This is a length of 2L, and this is the length of 3L. This is the problem we solved. We showed uh, one using two noded one element for each segment. This is segment 1, segment 2. This problem, and we obtained u tilde of x in the each segment by doing complete example problem with the assembly, substituting the boundary conditions, solving for the unknowns, and then obtaining u tilde of x in the each segment. That is what we have done, and this completes the chapter 2. Today we are starting chapter 3, and chapter 3 can be broadly classified into two groups. The first one is analysis of trusses and analysis of beams. I'll take couple of classes, like 2 to 3 classes, to analyze the trusses, and then I'll take another 2 to 3 set of classes to analyze the beams. So let's start the truss. So today we will talk more about the trusses. Okay. So what are the truss members? First, let us start from the truss members. So as you have a link element very similar to the bar, so the one what we have studied in the chapter 2 will help us to solve the chapter 3. So this is quite essential that the chapter 2 is a continuation, chapter 3 is a continuation of the chapter 3. So let us start the chapter on the trusses. So just give me a minute. So before I solve further, let me just tell you few things about trusses. The first few things are, let me draw a truss for you. This is an example of a truss, and the ends are simply supported, and let us say we are loading it by some amount. So generally you find these trusses in kind of some kind of workshops, and you also see trusses in the truss cutter bridges and so on and so forth. So the main points is all members are loaded. So what are the members? Let us see the members. This is member 1, member 4, member 5, member 6, member 7, and we ignore the self weight of the individual members. Next, all joints are pin joints. So if it is pin joints and anything this side of a member is axially loaded members. So these are pin joints and the thing, and this is pin joint support, and this is roller support. So, and these are the point loads. All joints are pin joints. The meaning of this is that these members, individual members, can rotate about the pin. So since this pins can rotate, it cannot resist the movement. It can, that means this joints there does not develop movements, or in other ways, summation m at a joint is equals to 0 at any given pin joint. So at all the joints, the moment, sum of the moments has to be equal to 0. This is one thing. Load always act on the joints. So even if you have certain uniformly load, what happens is all of the joint loads by partitioning it and giving it equally, or depending upon the ratios, we will split and distribute the loads, actual loads, into the point loads. So this is an example of a trusses. So all trusses are axially loaded numbers. We are ignoring self weight because if the self weight is there, bending has to be considered. We ignore the bending, so that's the reason self weight is ignored. And all the joints rotate, that means movement about any joint is equals to 0, and the load always act on the joints. This is the thing that we assume for any given truss structure. So for any given truss, these are the things. The shape of the truss can be different. The one which I have shown is only one example. There are several different types of trusses. Okay, so how do you model this using finite element method? And the second thing I want to ask is the first question: how do you solve or model this using FEM? This is first question. Let's say to solve this, we will recall we already developed the stiffness matrix of an axially loaded bar. So we have this information. And this is the first thing. But even though we have this thing, we cannot directly use it. Why? Because we have developed a bar element of this type. How do you model this bar? So the sub questions are: if I take a member, if I take this member, how many elements I need to divide for each member? Is it 10? Is it 20? Is it 1? That has to be discussed. So for that, what I would suggest is, in all these things, each, okay, let me write the, how many elements are required for each member? The answer is, this is the question, one element per member is sufficient. Why? Because the bar element has both the ends as the nodes inside thing is a axially loaded member, so that is sufficient. So one element per member is sufficient. But is this sufficient? No. So then why? Because the question is, in truss we have inclined member. Let us see what are the inclined members. So if you look at it, 2, 3, 5 and 7 are inclined, whereas 1, 6, 4 are horizontal, and we have already stiffness element for that. So that means, how do you handle these things? It is not in the horizontal, it is inclined to the horizontal. So if you have such kind of things, how do you construct the element stiffness matrix for such a inclined element? If we can model such an inclined element, then we are in a good shape to solve our solutions. So in order to solve these questions, we propose, I ask another question is, another topic we need to discuss is transformation of coordinates. If we learn the transformation of coordinates, then we are in a better position to deal with the inclined members by transforming the coordinates or axes. Okay, so if you answer this question, this will help you to deal with the inclined members. And since we already have the transformations as well as the single element stiffness matrix, we can develop the stiffness matrix of an inclined member. So to start with, the main important topic that I will start dealing with today this one. The first topic of the day which I want to discuss is transformation. So to deal with the transformation, let us say the original coordinate system is this one, and let us define a point A which is defined by x and y. Now let me define another coordinate system which is, I will call it as x bar and y bar, and the point of this A, or let me choose the other way around. I will choose this one as local axis and other one as, it's just a nomenclature, so it doesn't matter. So say this as global axis and this one as local axis. Now if I want to rewrite, how I would write it as, let's say this inclination is theta. Since transformation of coordinate systems, so once I do the coordinates, then we are in a position to handle the inclined beams. So let me start dealing with the transformation of my, so now let me write this x bar. My x bar can be written as x bar is written as x cos theta plus y sin theta. Similarly, y bar can be written as minus x sin theta plus y cos theta. So if you look at it closely, you can show that this x bar is because of, you can write it as this x bar is the sum of the x cos theta, which is this amount, which is this amount plus the other amount, which can be written as, this is the y. So anyway, this is standard things which you can figure it out, but still I will try to show it. So let me rewrite it, this thing. This total x bar can be written as sum of this plus sum of this one. Sorry, that is for the y. So okay, let me have a look. So let me rewrite it. So x cos theta. Anyway, you can easily write it in this manner from a standard textbook. So let me write it in this fashion. So you can write your x bar y bar as cos theta plus sin theta minus sin theta x and y. Okay, so after writing this, you can define a T matrix as cos theta so I can rewrite it as T times x and y. So this T matrix is called the transformation matrix. And one can write this one as A bar is equals to transformation of A, where A bar is in terms of x dash, y dash coefficients in the new coordinate system, and A is in the old coordinate system. So let us see the properties of T. So the properties of T would be something like this. T is an orthogonal matrix matrix. The property of an orthogonal matrix is, for orthogonal properties, inverse of a matrix is transpose of it. That is, if I want to invert this A, then I need to write it as T inverse of A bar. But since it is an orthogonal matrix, I can represent, that is, this says that orthogonal matrix is T inverse is equals to T transpose So we have this thing as a property of A. Using this as our property, what we will do is we will try to write the equation of, or the stiffness matrix of our given stuff. So now this is the important result. Okay, so let me just derive the other things. So the next one is, now consider the inclined member. If you consider this inclined member, you can see that let us say this is an inclined member which is at an angle matrix of an already horizontal member. The K matrix is even given by AE by L 1 minus 1 is 1 and 1. So from here, how to develop the stiffness of the other one? Okay, so for that, let us see this thing. Let's call this one as node I, node J, and this angle is theta. So we have the displacements for the displacement of this is ui, uj, which is only in the horizontal direction. But since this is in the vertical direction, the degree of freedom for this will be u bar I, v bar I, that is the displacement along this direction, the displacement along the other direction. Okay, because the displacement here, even though it is in the u, it will, sorry, let me rewrite it. It's in this u bar direction, in the for the I, when I split it direction depending upon my inclination. Okay, so we have 2 degrees of freedom. So in the local coordinate system, my degrees of freedom is only u bar, but if I split into the global coordinate system, my my things will be ui and uj, which will be in this direction, and vj. Let me rewrite it properly. So since this is u bar I, this can be split into a displacement along this direction and a displacement along this direction, which is u I and vi. Similarly, this u bar j can be split into a resultant of u I and v vj, uj and vj. So the resultant of these two will be giving you u bar j, and the resultant of ui and vi will be giving the resultant of ui. So that means if I want to convert this one into the global coordinate system, the global coordinate system is something like this, is the global coordinate system. The local coordinate system in this case is the inclination is theta. This is local coordinate system. Okay. Now I want to transform my variables, which is ui bar uj bar into, these are the things in the local coordinate system. I want to transform into the global coordinate system. So what I will do is I will try to use the transformation matrix to transform this local coordinate system into the global coordinate system. So using the transformation matrix, we can define from the above stuff which we have discussed. If you have these things in your bar system, you can get this one back using the transformation matrix, right? So the transformation matrix is given by cos theta sin theta minus sin theta cos theta transpose. So, but this is for the individual coordinates. So when we are doing it, this becomes little bit tricky. So what we need to do is we have to be very particular. We know each coordinate is splits into ui vi. So we need to do the transpose 0 matrix, 0 matrix, T transpose times ui vi uj vj. So cos minus sin plus sin cosine 0 0 0 0 0 this will also something like this times cosine. Here these zeros represents, this is v bar I and this one is v bar j. Anyway, those are not there because in the axial deformation you can only see this one and the perpendicular quantities are 0. This is anyway 0. This displacement is 0 because this is only axial member. The perpendicular deflections are 0. You can write it in this manner. So using this special transformation matrix can convert the local things, these are the local transformation. This is global. Sorry. These are local degrees of freedom, and this is global degree of freedom. So this transformation is useful to deal with the trusses. So anyway, first let's take an example of truss, use the above things later to kind of solve the problem. So first one, let us so let us take solve a simple truss problem. Let me take the example of it properly, and then we will solve that problem. So seventeen, 18. So this member consists of, or let me put this one as a roller things, it doesn't matter. So this is number 1, this is number 2, number 4, and 5 elements are there. These 5 elements are modeled as element element 2, element 3, element 5. So let's number the nodes as 1, 2, 3, or let me name it as A, B, C, D. So this is A, B, C, D. So we have this kind of a configuration, and we want to, this is the element formulation, element discretization, and this is for the finite element manner. Anyway, we will try to kind of frame the things. So let us, I mean, we will try to solve this one analytical at a later point of time, but let's solve it in the finite element sense. So first is the boundary condition here. U, this is U and V directions. So here UD is equals to 0. Sorry, UD we don't know. Since it's a roller support, this it cannot go inside the things, so this is constraint, horizontal movement is constraint, so UD equals to 0. If you come here, it cannot go in this direction, it cannot go in that direction because it's a pin joint. UA equals to 0, VA equals to 0. Here the things are UB, VB, UC, VC. We don't know what is VD, but only things we know is UD equals to 0, UA equals to 0, and VA equals to 0. So what we will do is the element stiffness matrix for the element 1 is given by 1 minus 1 minus 1 1 with UA UP. But I want to rewrite this fellow in a manner that I want to represent a new k element of the 1 in the two-dimensional things as one, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, 0. So if you looked at it, what we are doing is we have in 2D truss members, in the 2D truss structure, or you should say 2D truss structure, it is in 2D plane. If it is in 2D plane, at every node we have 2 degrees of freedom. The 2 degrees of freedom are the first one along x, the second one is along y. So that is u and v. Whereas for 1D bar structure, 1D bar structure, we had only u, a and b. So you have ua, ub. The other things are ignored because va is equals to 0, vb only you have x as a prominence. However, if it is this member is in an inclined plane, as I discussed earlier, if this is in the coordinate transformation, and we showed that our x bar plus c s minus s c times x and y, where c is equals to cos theta, s is equals to sin theta, and let's say x is global axis and x comma y is in global axis, x bar comma y bar is local axis. So that means what I'm going to show is, if similar to this, we can write any given coefficients a bar is equals to c s minus s c into a, and I call my a bar as transformation times, if I know global, I can write my local in this manner and vice versa. Okay, so that is what we have done. Or if we want our local, then it is inverse time of a bar, but since it's an orthogonal matrix, we define it as this. This is what we have learnt so far. This I have repeated so that for the continuity. Now what I want to do is, I want to develop it for a beam, for a bar. So for a bar who has inclined members compared to this one. Okay, this one has UA, this is UB, and VA is equals to 0, VB equals to 0. This is horizontal member. For horizontal member, my K stiffness matrix is given by AE by L 1 0 minus 1 0 0 0 0 0 minus 1 0 0 1 0 0 0 0 0. That means my force vector RA, so let me call it as the forces are, this as P, sorry, this as RA and this as QA. So RA, QA RB QB AE by L 1 0 minus 1 0 0 0 0 0 minus 1 0 1 0 0 0 displacements which are given by UA, VA, UB, VB. This is for a horizontal case, it was very simple. For this horizontal case, this is the thing. But now I want for an inclined member. I want for this member. So for that, what I'm thinking is, if I have this member like this, and if I define a coordinate system here, and in the coordinate system, if I write u bar a and v bar a, in this inclined axis, this solution is same as that of the horizontal system. So let me rewrite it. Let me cut short bar qa bar r b bar q b bar, and I'm writing the solution in this because I have only u bar a and u bar b, and I will only have corresponding reactions ra bar. Q is zeros, but still I will have to represent is r bar b. So is equals to ae by l 1 0 minus 1 0 0 0 0 0 1 minus 1 0 0 0, sorry, 1 0 0 0 0 0 times my degrees of freedom are in the inclined system, which is UA bar, UB bar, DB bar. But I know that I don't have my degrees of freedom in this when I'm solving the rest of the system. I'm having my system as what is UA and what is VA, and I want to know in this global coordinate system what is UB and what is VB. So I want to convert this fellow, I want to convert this fellow, and I want to see if this becomes RA, QA, RB, QB, that is the forces are in this for the inclined member, and the displacement is also in the horizontal and vertical, UA, VB, VA, UB, VB. What is this new K? What is this I want to find out? If I have that, then I can use the same thing to handle any given inclined member. To do that, let me rewrite it in this easiest form. So the easier form is, let me call this as, in a local system, R bar is equals to K times of T bar. Okay, let me call this one. These are the displacements, these are the forces. These are the displacements. This is the stiffness. Now we know that the transformation between, this is written in the local system of that one, but we know that R bar is equals to transformation times R. Similarly, the D bar is transformation times T. So I replace these two here. So if I try to replace these two here, then I'll get something like this. Let me call it as local times t times t global, right? This is what I can replace it, but that is nothing but r times t inverse of k l t d. But we know that since t is an orthogonal matrix, we can define it as T transpose K local times T times of T. So this is the T, what we defined gives us the T for this case would be for a one node, for one point would be for one node or one point is C S minus S C. But here when we are dealing with, we have 2 points, but the both ends of uh, the member. So our T for a bar would be C S minus S C 0 0 0 0 0 0 C S C. You need to know that this is for a 2D bar. That means it is in a plane of x and y. The bar is something inclined. Sometimes it may be that it may be in the bar is in the xy plane. Sometimes you see that for a bar in 3D plane, that means your plane is like this. This is x, this is y, this is z direction, and your bar can be inclined something like this. It is in both, it has x, it has y, it has, let me draw it like this, it has also, it has x, it has y, it is also the z direction. So it has x a, y a, z a, and x b, y b, z b. So that means it is inclined in the 3 dimension. In the 3 dimensional, the transformation matrix T for such things is pretty simple. Okay, assume that even though the bar lies in the 3 dimension, um, and the rotation is only in the 2 dimensional plane, because you don't have in the 3rd dimensional plane, you can write it as C S 0 minus S C 0 0 0 1, and this is C S 0 minus S C 0 0 0 1. all other things are zeros. So this would transform, this T matrix would transform from x bar A, y bar A, z bar A, x bar B, y bar B, z bar B, from x, y, z, A, and x, y. So for point is different, for a two-dimensional bar it is different, for three-dimensional bar is different. They all the three are developed from the same thing, just by looking into the consideration that whichever is inactive or not rotating, we will put a zeros things in that directions. Okay, so these are the transformation matrix if you're dealing with a point transformation or a bar transformation in a 2D or a bar transformation in a 3D plane. Now using this transformation, let's get back to our main thing. What we said that now what we got from the previous thing is R is equals to T transpose of K local times T times D. But I can write this thing as R times K times D. That implies my K in the global system can be defined as T transpose K local times the T. So let us do it for this our given case. So for our case, what will happen is our K local, as we discussed earlier, for a 2D bar is AE by L 1 minus 1 0 0 0 0 0 0 0 minus 1, sorry, minus 1 0 1 0 0 0 0 0. This is your K local matrix. So when I multiply my K local matrix with the transformation matrix, what I will get is something like this. So K global is given by C minus S minus S C, this is plus S 0 0 0 0 0 0 C S minus S C 0 0 transpose AE by L 1 0 minus 1 0 0 0 0 0 minus 1 0 1 0 0 0 0 0 times T, which is CS 0 0 minus S C 0 0 0 0 CS 0 0 minus SC. If I multiply this file properties, on multiplication, we can see that we'll get something like this. The K matrix is given by AE by L times C square CS minus C square. I'm just doing it quickly because of lack of time. You can just do this computing yourself later point of time. S square minus cs minus s square minus c square minus cs c square cs minus cs s square. This is your global stiffness matrix where c is equals to cos theta, s is equals to sin theta, and theta is the angle between your global to local axis or inclination of the bar with the global axis. So all you need to know is your theta. Once you know the theta, then you are determining the entire stuff. So with this, we'll make use. So this is so generic that theta can be anything. For example, let theta is equal to 0. So this is an inclined that implies it is a horizontal member. We know the horizontal member, it should give back your original things. So substitute c cos 0, c is in this case is cos 0 1 and s is 0 in this case. For that it will represent back. So if you look at here, it is we can write this fellow as 1 1 0 minus 1 0 0 0 0 0 minus 1 0 0 0 sorry, this is c square, so this has to be different. C square is 1, so this is 1 0 0 0, which is nothing but what we have done in the previous case. So our k has been reduced to the same thing. Now let's say our element is 90 degrees. If there is an element is in the 90 degrees, then our k will become something like this. So it is now c is equals to 0 and s is equals to 1, then we'll have 0 0 0 0, then we will have 0 1 0 minus 1 0 0 0 0 0 minus 1 0 1. Similarly, if you take any, sorry, with this ae by l, similarly if you take a 45 degrees, then s is equals to c is equals to 1 by root 2. We can show that it is equals to k is equals to ae by 2l 1 1 minus 1 1 1 1 minus 1 minus 1 minus 1 minus 1 1 1 minus 1 minus 1 1 1 is your ae by l into ae by l for a k matrix for a 45 degrees. So for any given theta, you substitute S is equals to sine theta and cos theta, you can obtain your K matrix for the inclined members. Now since we know this inclined members, now we are in a better position to handle the any inclined members, because in a previous example we had a member which is in this orientation, one is in this direction, one is in the other orientation. All we need to know is, if we know the corresponding thetas, we could easily determine our K matrix for that corresponding theta. So let me summarize of what we have done today is, we said that we know K for bar element in 1D, that is AE by L, 1 minus 1 minus 1 1. We use this one, then we know we got the transformation things between local and global, that is we showed that our R bar A bar is given as transformation times L, sorry, transformation times A, and this transformation, depending upon 1D, 2D and 3D, the shape would be changing. And if you know this transformation between a local and global coordinate,